All right, everyone, we're going to get started soon. So before we do, let me remind everybody that for your final projects, we will have the final project presentation starting next week. So the GSIs are putting together the schedule now. We'll try to get the schedule sent to you today. If you have any conflicts, please make sure to check the schedule right away. Let us know if you need to switch to the other day or something like that. But everybody will be presenting either Monday or Wednesday next week. The presentation will be 2 minutes in length so that everyone has a chance to present. So please give a quick overview of your project and the results. And then in the final project assignment, it has the due date for the actual report, which will be quite a bit later during the final exams period. Okay, so today it's my pleasure to introduce John Schulman. John did his PhD here at UC Berkeley with Professor Peter Abeel, and during his PhD, he pioneered some of the most popular policy gradient methods today, including trust region policy optimization and proximal policy optimization, which we'll talk about today. And John is currently a research scientist at OpenAI.
All right, thank you, Sergey. It's a pleasure to be here. So I'll talk about proximal policy optimization, also known as PPO, which is kind of the latest in this sequence of policy optimization algorithms that I've been working on with colleagues. And I'll first try to give a bit of intuition for the algorithm and the update we propose, and then I'll talk about some applications of this algorithm where it's used as a building block for something else. So first, a little background on policy gradient methods. So in these standard reinforcement learning tasks, you're trying to maximize the expected sum of rewards in a POM-DP. So this is a natural formulation for lots of control tasks, but also various machine learning problems that aren't usually thought of as reinforcement learning can be cast in this framework, like sequence tasks, like machine translation, where you have some kind of, you want to write down a non-differentiable loss function. And also anywhere that you have to make hard decisions, like if you have a hard attention model or you want to do conditional computation, it makes sense to apply, to cast this as a POM-DP or as an MDP and use policy gradient algorithms. And policy gradient methods have been used for these kind of problems. So first, let's review just the vanilla policy gradient methods that we're trying to improve upon. So in policy gradient algorithms, you're doing gradient descent using some noisy estimator of the policy gradient. And this estimator has the form grad log probability times the advantage function at each time step. And this involves some expectation where you're taking an expectation over trajectories that you sample where the agent interacts with the environment, and you're averaging over time. And usually people, so the key problem here in getting a good estimator is to estimate the advantage function, which tells you whether this action was better or worse than average. So there are a lot of different methods for getting better estimators of the advantage function. Typically, we use biased estimators. We get lower variance estimators at the cost of introducing bias. So as some examples, A3C proposes one kind of biased estimator for the advantage function where you collect one chunk of time steps, and you use the value function at the end of that segment to account for the future rewards. So anyway, and we'll talk about, well, there's another one where you sort of do a generalized advantage estimation is another version of this where you have, it's kind of similar to TD lambda, where you have this lambda parameter that determines how far into the future you're looking at. So What's good about policy gradient methods as opposed to other RL algorithms like Q-learning? Well, you're optimizing what you care about. So what you care about is the expected returns of your policy. So it would be nice if we can actually optimize that directly rather than optimizing something else and improving our policy as a side effect. So nice thing about policy gradient methods is you optimize what you care about. The bad part is that they have worse sample efficiency than Q-learning. And I would say overall, in terms of the classes of deep RL methods, Q-learning type methods usually have the best sample efficiency. Well, this is in the set of model-free RL algorithms. Q-learning would be the most sample efficient, and policy gradient methods are less. They're in the middle, and evolution strategies or derivative-free optimization is the least sample efficient. And there's also some issues. So for vanilla policy gradient methods, one issue is that it's hard to choose the step size that works throughout the whole optimization process, because you have to be careful. Well, it's harder than in supervised learning because the distribution of inputs changes over time. So as you update your policy, you start seeing a different distribution of observations and a different distribution of rewards. So since the statistics of the inputs are changing, it's hard to choose a step size that'll work for the whole optimization process. So these kind of vanilla policy gradient methods can be made to work well, but they tend to be sensitive to hyperparameters and architecture choices. On continuous control problems, the vanilla methods lag other methods like trust region policy optimization and PPO, which I'm about to talk about. Okay, let's just review trust region policy optimization. So the idea here is to improve the vanilla policy gradient method in two ways. First of all, choose step sizes in a more robust way, so you have like a more intuitive hyperparameter to choose that works over the whole course of the optimization. And second, just get a little bit more information out of each bit of data that comes in. So in a vanilla policy gradient method, you're only using each piece of incoming data to compute one gradient, and then you throw it away. Whereas it seems like you should be able to get more out of each bit of data. So, and in particular, the vanilla policy gradient methods are like any gradient descent method, is dependent on the parameterization of the policy. So if you have a poorly scaled problem, meaning the gradient is much bigger on some parameters than on other parameters, you might have really slow improvement. And that means your algorithm is going to have worse sample complexity. If you're just if you have this poorly scaled problem and you're just bouncing around in the high curvature directions of your objective function, then you're not going to make much progress per amount of data sampled. And in RL, we sort of assume that the main cost is interaction with the environment. So so that would make you have worse sample efficiency. So anyway, TRPO is trying to address some of these problems. So the basic idea is we write down this objective. Objective function, which kind of looks like an importance sampling estimator, and in fact, it's quite closely related to importance sampling. So we want to maximize this expression that looks like expected advantage under your new policy, which is pi sub theta. And we do this subject to a constraint that we're not moving the policy too much. So the basic setup is we collect some data from our policy pi sub theta old, and then now we want to update it to get our new policy pi sub theta. So we take the data we just collected, we write down this constrained optimization problem, we solve it, and that gives us our updated policy. And in this case, we have some kind of importance sampling looking objective, and we're subject to a constraint on the KL divergence between the new policy and the old policy. Okay, so TRPO is defined using this hard constraint on the policy update, but it's also worth considering using a penalty instead of a hard constraint. So, instead of saying the KL divergence between the old policy and the new policy has to be less than delta, we say we're just going to add a penalty. We'll subtract out a penalty for the KL divergence. So the reason why we initially proposed to use the hard constraint is just that it's an easier hyperparameter to choose. So delta is an easier hyperparameter to choose than beta. And one main reason for that is that delta is a dimensionless quantity, the KL divergence between two distributions. So it's measured in bits, and it doesn't depend on the scale of the rewards in particular. Whereas in the second version with the penalty, the beta has to depend on the scale of the rewards, and it has to have units of rewards per bit. So basically, beta is telling you the trade-off between rewards according to your advantage function and bits of KL divergence between your new policy and your old policy. So it has units of rewards per bit. So it might depend, the proper choice of beta might depend on the scaling of the rewards. Of course, you can normalize your rewards in some way, and actually that'll make the second version work a lot better. So more recent work that uses penalties instead of constraints usually involves normalizing the rewards, and that's sort of a key piece of the algorithm. So, of course, these two versions are equivalent in a sense because if you have some optimality point for the first version, the delta constraint version of the problem, this is also an optimality point for the penalized problem. So there's an equivalence between these two versions. But as I said, the big difference is that it's easier to choose the delta hyperparameter, the hard constraint.
Do we ever maximize these to completion? Like we never reach the optimum point ever, right?
Oh, right. Yeah, so first, yeah, I've just written down these optimization problems, and I haven't said anything about how we actually solve them. And the question was, do we actually solve these to completion, or do we just do some kind of partial solution? Yeah, so in practice, we don't solve these to completion. We solve them partially. Of course, that's sort of a sensible thing to do because these are just surrogates for what you actually care about anyway. These problems aren't, this is just like, we're writing down this constrained optimization problem because it's the objective is like a local approximation to your true objective function. So we're just trying to improve the local approximation a little bit, and it doesn't necessarily make sense to optimize it all the way. Let's see. Do I talk about the actual? Oh, I don't talk about how. Did you guys have a previous class on that covered TRPO?
Yeah.
Okay. Yeah. So I won't talk about TRPO anymore. But actually, I think the nice thing here is that you have this. So there's this. The idea of the theory behind TRPO is that. You can think of it as a minorization maximization algorithm where, so let's say this is your true, well, okay, let's say this is your, in 1D, let's say here's your parameter theta. This is your true objective function. Let's say we're starting over here. When we make our local approximation of the objective, maybe it looks something like, maybe it looks like this. So it's got the right gradient, but if you maximize it all the way, you'll go out to infinity. But then if we take this local approximation and we subtract out a penalty, we get something that's a lower bound on the true objective. Then if you make, as long as you make any progress on this this pessimistic version of the objective, then you're guaranteed to make progress on the true objective. So as long as you're sufficiently, if you choose a sufficiently large parameter beta, you're basically guaranteed to actually make progress on the true objective. Of course, there's like bias and everything in your gradient estimates, so that's not actually true in practice, but that's sort of the idea. So that's why it makes sense to just solve this optimization problem partially. Yeah.
I guess my follow-up was more like the equivalence between the two is
Oh, yeah.
questionable because it's only partially optimized and they're only equal at optimality.
Yeah, yeah, that's true. Yeah. All right, so okay, so why aren't we done with TRPO? Well, unfortunately, empirically it's worse than the vanilla policy gradient on certain problems, especially. And this is for reasons that aren't fully understood. On Atari, it's never really done as well as A2C or A3C when those algorithms are well tuned. So for some reason, when there's something going on that that isn't quite captured by TRPO, and in other cases. Well, the sample complexity still has lots of room for improvement. It's still, even though it's more sample efficient than vanilla policy grading methods on many problems, there's still a lot of room for improvement. So actually a big reason why we'd like to improve on TRPO is it would be nice to have a first order method where all you have to do is do gradient descent on some objective. As opposed to doing conjugate gradient as in TRPO, where you have to do these Hessian vector products. So if you're just doing pure RL, then it's okay to have this slightly more complicated method with second order optimization. But then if you're mixing a bunch of things together in the same network, it doesn't, then you start to, the CG optimization starts to run into problems. Like one issue is that let's say you want to use a single network that has two outputs, one for the policy and one for the value function. In TRPO, you're using this KL divergence constraint on the policy to limit the size of your update, but that constraint doesn't say anything about how much to update the value function. There are various ways you can address this, like you can add some other kind of distance on the value function to prevent that from changing too much, but it's going to be kind of ad hoc. And in general, this formulation isn't that good when you're trying to mix together a bunch of objectives, only some of which actually involve the policy probabilities. Also, it doesn't accommodate having any kind of noise in your architecture, such as dropout. On the other hand, none of the methods seem to benefit from that so far. We want to be able to enforce many soft constraints as opposed to just a single soft constraint. So as I said with the value functions, we don't want the value function to change too fast either. But now when you have the CG, the whole derivation we went through for conjugate gradient assumes you only have one constraint. And if you want to have multiple constraints, then you don't have as neat of a way to solve the problem. And also, being simple to implement is actually pretty important, especially when you scale things up and your algorithm gets complicated in other ways. Yeah.
I don't understand why dropout is specifically the first order method.
Oh yeah, so the question is, why is dropout an issue? I guess you could, you could do dropout with TRPO if you keep your dropout mask frozen. Yeah. Yeah, that's true. On the other hand, if you're doing, if you have like random variables in your network, then if you're just doing stochastic gradient descent, it's fine because every single step is a stochastic gradient, and as long as they have the right expectation, you're fine. But if you're doing a second order method, you have to be more careful because you have to make sure like for CG, you need to make sure every time you do a Hessian vector product, you're keep freezing all of those variables. Yeah. Okay. Okay, so what we want to do is write down some objective, and then we can do SGD on that objective, and we'll get a good policy update. So then the question is, what loss should we actually optimize? So let's just look at the policy gradient. Let's just look at policy gradients. So we've got this grad log probability times advantage. So you can get that by differentiating the loss that looks like log probability times advantage. But the problem is, you don't want to optimize that objective too far, or you're going to do too big of an update. And this has the same gradient as this objective that has a probability ratio. So when pi theta equals pi olds, these two things have the same gradient, and you can that's easy to check. So that's another potential objective you can use. But this also has a similar problem. If you just try to maximize this to convergence, whenever you have a positive advantage, pi sub theta will be driven to 1 or to infinity if this is a continuous problem. And whenever it's a negative advantage, pi sub theta will be driven to 0. So you're going to do too big of a policy update if you try to just optimize this thing to convergence. So now let's just go back to TRPO, and we already talked about one way of fixing this problem, which is to use a KL penalty. So what I said in the previous slide is that the problem with that is that it's hard to choose this KL penalty coefficient. It's hard to choose that hyperparameter, and in particular, there might not be a single value that works over the whole course of the optimization. So, okay, well, we can fix that problem by just adapting the penalty coefficient. And that's one simple way of implementing, that's the first version of PPO. So in this version, we write down the usual objective that has probability ratio times advantage function minus constant C times that should be beta, because I'm using beta here. It's a typo. So we have the importance sampling. We have this objective minus coefficient times KL divergence. And we want to, so each iteration we collect a bunch of data. So we get t time steps or n trajectories. We estimate the advantage function at every time step. And then we do SGD on this objective for some number of epochs. And here's the new part, which is pretty simple. If the KL, okay, so you choose a target KL divergence, which you're going to keep constant for the whole algorithm. So let's say you choose 0.01, and that means every iteration we want the KL divergence between the new and the old policy to be about 0.01. So the way we do this is, if the KL divergence is too high, we increase our penalty coefficient. So it's like we tighten the sort of tighten the constraint. And if the KL divergence is too low, we decrease the coefficient. And then we don't re-optimize. So we still didn't hit our target. We were either above it or below it. But then hopefully the next time we'll be closer to the target. And then you can just choose some sensible, then there's some parameters of exactly how you do this update. So the way I would usually do it is to say, if the KL is more than 2 times your target, then you increase the coefficient by 1.5 times. And if it's less than 1/2 your target, you decrease it by a factor of 1.5. So I found that 2 and 1.5, those parameters don't really matter very much. So as long as you choose sensible parameters, it'll roughly track the target. Okay, so that's sort of the easiest, the most straightforward version of PPO. Or that's the most obvious one from TRPO, from looking at TRPO. But actually, there's another version which is we found to actually work better, and this is the one that we got the best results from, and it's actually even simpler than the other version. And it's a little less intuitive, but I'm going to try to explain the intuition behind it. So let's define R sub t as the probability ratio at time t, meaning action probability under new policy divided by action probability under old policy. So at the starting point, before you've updated your policy, the ratios are all equal to 1. And recall that the TRPO objective uses this objective, which is just expectation of this ratio times the advantage function. So here's the objective that we're proposing now as the improved version of PPO. So you take the we take this old this old objective, which is probability ratio times advantage, and then we also take a version where you clipped the importance ratio. So we took the importance ratio and we clipped it to be between 1 minus epsilon and 1 plus epsilon, where epsilon is, say, 0.1 or 0.2. So that gives us two different objectives we might want to maximize. And we just take the point-wise minimum between these two objectives. So this is like point-wise minimum means we're being pessimistic. So we take whichever one is worse according to our optimization, according to our criteria, which is maximization. Okay, so that's what the objective is. I mean, you might think you want to clip the importance ratios because you don't want the importance ratios to go too far away from 1. That's sort of part of the intuition. And I'll explain why we want to take the minimum between the unclipped and the clipped version. So let's look at a single time step. Let's look at this clipping objective for a single time step. And on the x-axis, let's look at the probability ratio, and y-axis, let's look at this single term in the objective. So we start off where the probability ratio is 1 before we've updated the policy. And let's say the advantage is 1 here. So that means this action had positive advantage. So right around the starting point, the objective is nice and linear. But then if the importance ratio goes past 1 plus epsilon, we flatten it out. So what that does is it says there's no incentive for increasing the probability past 1 plus epsilon. So we take away the incentive to drive this positive advantage action to have higher probability ratio than 1 plus epsilon. Now, let's say you had an action with negative advantage. Well, at the starting point, this objective term is nice and linear. But then if you were to decrease the action probability to less than 1 minus epsilon, it gets cut off, meaning we remove the incentive to lower the probability of this action below 1 minus epsilon. So that's what the clipping version. That's what the clipping does. Now, so we basically remove the incentive to drive the probability ratios away from 1 too far. Yeah.
So when you do this clipping, doesn't it kind of harm the convergence of the algorithm?
Yeah. So question.
Converge with the clipped version?
Yeah. So the question is, when you do clipping, doesn't this harm the convergence? Yeah. Conceivably you're making the objective much more non-smooth when you do the clipping. On the other hand, we're getting stochastic gradients anyway, and I don't think the non-smoothness that you get from the clipping here is worse than, say, having ReLUs, which are also have a point that they're non-differentiable. So I think this works for the same reason that optimizing neural networks with ReLUs works. Yeah, the objective is non-smooth for a single term, but then when you have a lot of terms, you add the objectives together and you get a smooth objective function. And I'll actually show you a plot next that sort of illustrates that it's actually smooth when you add together a lot of these terms. Another question?
So do you see clipping happen near the beginning of one step, or does it take multiple steps before the clipping actually starts happening?
Yeah, so the question is, do you see clipping right away, like after one gradient step, or does it take multiple steps? So usually as a diagnostic, I do look at what fraction of the points, the time steps are getting clipped. And usually it doesn't start getting clipped. Usually they start getting clipped after multiple steps. That's right. So the first step is like pretty much in the policy gradient direction. And then after a few steps, it gets to some region where like some fraction of the samples are being clipped and some fraction aren't. And the clipped ones give you zero gradient, obviously. So you don't want too many of them to be clipped, but yeah. Okay, so basically the clipping removes the incentive to drive the probability ratio too far away from 1 in the direction that the objective is trying to pull it. So the objective is trying to increase the probability of this action and trying to decrease the probability of this action. The reason why we do the point-wise minimum between the clipped and the unclipped version is that, let's say, we also we don't want the clipped version to hide. We don't want the objective to hide if you're making a certain point worse. So in the unclipped object, let's say you have a point with negative advantage, and let's say we're using the clipped probability ratios, and then you radically increase the probability of that action. Then if you just used the clipping on the probability ratio, you're going to think your objective, you're not going to notice that your objective isn't going to account for this. It's not going to think, oh, this is really bad because I just increased the probability of a negative advantage action. Because if you clip the probability ratio, you're not going to see that. So, but if we take the point-wise minimum between the clipped and the unclipped version, then you see the bad points, like where your objective, you see the bad points where you're sending the probability in the wrong direction, but you also ignore the good ones where you're trying to send the probability too far in the right direction. That was kind of wordy, so let me show you, oh, actually 2 slides from now. Yeah, let me show you this, which hopefully will illustrate it. Let's say we have a single state. Let's say you collected a bunch of data and you have the same action pair that appears twice. But one time the advantage estimate is positive and the other time the advantage estimate is negative. So what we would like is we want our objective to just penalize you from moving in either direction. So it should penalize you from either increasing or decreasing that action probability. So let's look at the positive advantage term and the negative advantage term. So the positive advantage term looks like this, meaning it's telling you to increase the probability until you get to the clipping point. And the negative advantage term is telling you you're starting out here and it's telling you to decrease the probability until you get to the clipping point. But then when you add them together, you get this thing that looks like a kind of approximation to a parabola where it's telling you don't move in either direction too far. And actually, I'd say that the real one other explanation for why this works is if you take any kind of, if you've heard of F divergences, who's heard of F divergences? Yeah, so F divergence means you have some kind of function of the probability ratio. So it's a measure of the difference between 2 distributions P and Q. So this is how the F divergence is defined, and F has to be some convex function of the probability ratio. So KL divergence in both directions, total variation divergence, and other probability distance metrics that people commonly use are special cases of this, where you choose a particular value of F. So basically, if you take any convex function of your probability ratio, it'll work somewhat like a distance between distributions. So you can see with this objective, well, actually, it's concave with we're doing maximization and we're taking a concave function. But if you were to, basically, you're taking some concave function of the probability ratio here. And so basically, it's going to look like a distance. And if you put in any other concave function, it's going to act similarly. So that's another interpretation for what's going on. That basically it's applying some kind of, it's working like some kind of funny F divergence on comparing the new policy to the old policy. Okay, so here's another plot that sort of illustrates how even though it looks like this objective is non-smooth because of the clipping, it actually might be smooth when we're averaging over a lot of data. So for this plot, we computed a policy update, and then now we're looking at what happens when you interpolate between the old policy and the new policy. So you just look at that one-dimensional space and you move along that line and see how your objective changes. So of course, KL divergence just looks like a quadratic function like usual. It's increasing sort of quadratically. Then let's look at our objectives. So if we just look at the this objective probability ratio times advantage, this is obviously, at the starting point, it's giving you the policy gradient. But as you go out to, if you go out in this direction, in the policy gradient direction, it keeps improving. So if you just optimize this thing, you'd go out to infinity here. Then let's say we just clip the probability ratios, but we don't do this pointwise minimum thing. Then we get this green curve, which sort of levels off as you would expect, meaning as you're increasing the, as you're going too far, most of your probability ratios are getting clipped, so you're not seeing much improvement to the objective. But it does keep increasing. So especially if you use an algorithm like ATOM, which is rescaling your gradients, you might still end up going out to infinity if you keep optimizing this green objective. But then if we look at the clipping objective, it's this nice looking parabola kind of curve, which has a maximum here. So that's showing you that if you optimize this objective with the clipping, it's actually you're actually converging to some optimum, which involves a reasonable policy update. Any questions? No. Okay, so just to review the pseudocode on this, it's so each iteration you run your policy and collect some time steps of data. You estimate the advantage function at all these time steps, and then you do SGD on your objective for some number of epochs. And so that gives you your updated policy. So that's nice. We just removed the whole adaptive KL coefficient thing. So actually, this is very simple to implement if you just have a if you just have A2C, all you have to do is change the objective function and do more steps of gradient descent. And you can either do this as SGD, where you're sampling mini batches, where you split up your data into a bunch of mini batches and iterate over them, or you can just do full batches. In my experience, if you do full batches, it takes more passes over your data to get the same result, but usually you can get just as good of a result. So yeah. And okay, so how are the empirical results? So it's a bit better than TRPO on continuous control. It's much better on Atari. So TRPO, we never got that good results on Atari, whereas PPO, we do get good results, which are much better than A2C. And the nice thing about PPO is, since you're just doing SGD on some objective, it's compatible with doing other things along with policy optimization, like having a network with multiple outputs, like you're doing prediction along with control. And also, it's compatible. This is easy to implement with RNNs. In contrast to some other methods, which aren't so easy, which are also more sample efficient, but not so easy to implement with RNNs. Like there's another method that has nice sample complexity results that uses it does natural gradient by estimating a, it's called, uses this method called KFAC, which approximates the Fisher information matrix. And this method also gives you a big improvement over A2C, but it's harder to implement with RNNs. That's called ACTR, ACKTR. Okay, so just to show some plots illustrating this. So on continuous tasks, it's a lot better than TRPO. Well, it's not a lot better, it's a little better. So we use these very small Mujoko tasks that you might have seen on the home. Did you guys do homework assignments with these tasks? Yeah. Yeah, so it's, so the funny thing is for all these algorithms, the performance is pretty variable from trial to trial, and you always find that in some tasks, well, the sorting of algorithms differs by task, but overall PPO seems to do the best. And especially on the larger tasks, I'm not showing the harder tasks here, but it seems like it does nicely on the larger tasks, like with high, like humanoid locomotion. I'll show a video of that shortly. And on, so on Atari, it's about the same as the best policy gradient methods. So it's a lot better than A2C in terms of sample complexity, and it's about tied with Acer and ACTR. I think it's a favorable trade-off in terms of performance versus complexity, like code complexity and time complexity. So let me show a couple videos. So here's a video. We trained this humanoid to where the objective is to run towards this red ball. And so the reward function is basically how much progress it's making towards the red ball. We're controlling it in terms of joint torques. And it's being pelted by these cubes as it's going along. So this, I would say this version where it's getting pelted didn't work perfectly because sometimes it has trouble getting up off the ground, but overall I would say it's pretty good. It's pretty robust to getting pelted, and it's pretty cool that it can, the same policy can get up off the ground and run. And this is like just a single, this is just a network with a feed-forward network with 2 or 3 hidden layers of something like 64 hidden units. So it's just like a tiny ReLU network that's learning this thing. So it's actually kind of surprising that you can get such a complex-looking behavior from just a tiny ReLU network. So actually one funny thing you can do with this is once you've trained it to run towards the ball, you can make the ball interactively controlled, so you can control it with your keyboard. Now it's not guaranteed that this is going to work because now you're kind of out of sample because you're seeing a distribution of like ball movement that you've never trained on. But in practice, it's actually, especially when you take away the balls, the cubes that are being thrown at the robot, it has no trouble doing it. So you get this humanoid that you can control with the keyboard. And it seems extremely stable, so I've never seen it fall over.
Can you self-play a keep away game?
I'll talk about self-play in a moment, yeah. Okay, so now, next I'm just gonna touch on a couple, actually, let's see, we have until 12, so let's just take a 3-minute break, and then I'll start again at 11:25.
How much does the baseline matter for this?
Matters a lot. Yeah.
Which one did you use for these? For the ones you showed, the videos?
This is just a MLP, same kind of network as the policy. So it's a MLP approximating the value function. Actually, the best like learning curves I've seen on the humanoid are from the PPO plus QPROP. So Matthias did some experiments where he did PPO plus QPROP, and that gives you like really fast learning curves on the humanoid.
Yeah, that makes sense. There were a bunch of newer work that came out, like one from the group that did SVGD.
Yeah.
Oh.
Stein something.
Oh, yeah.
Control variants. And there's another iClear submission with some funny control variants. Have you guys tried any of those?
No, I've been meaning to check them out. You, like one of them is the bar.
Yeah.
Yeah, I haven't looked at it.
Shane thinks that the QProp should still be very competitive. And based on their results, I think he's probably right, but I haven't seen anybody like do a rigorous comparison.
Yeah. Yeah, Matthias Muller did some experiments, or Matthias Clapper did some experiments where he just tried PPO like out of the box and PPO plus QProp out of the box.
And when you say QProp, do you just mean Q function approximation, or do you mean the off-policy QProp with like the Q learning update rule?
I think he did. Oh, I think he did the whole thing with the off-policy training of the Q function.
Yeah.
And then the sign did the sign thing.
Okay. Because in principle, one could do a very simple version where it's just a Q function based, like an MLP fit to the Q function, the same way you fit the value function.
Yeah.
Not yet.
Actually, I don't know how. Yeah, does that one?
I don't know. I've never tried it. I don't think Shane ever tried it either. Because he set up QProp on top of like an EEG type thing. So I don't think he ever tried just fitting the Q function the same way you fit the value function.
Oh, actually, yeah, I'm not. One confound is I'm not sure. So I've heard of another set of experiments where, so Oleg, my collaborator, tried just using a longer replay buffer for the value function. So you just fit the value function on more data.
So you pretend like it's on policy.
You pretend it's on policy.
That works better.
And that actually helps a lot too.
Which is funny because you're not at that point. You're not necessarily reducing variance. But I guess you bound how much the policy changes, which bounds how much the value changes, right?
Yeah.
Are you keeping track of your?
Oh yeah, I guess time's up. So.
When you're picking the actions, are you choosing the max or a soft max or double max or something?
Oh yeah, so the actions are sampled from a Gaussian. So the neural network is outputting the mean of the Gaussian, and then you have a separate set of parameters for the standard deviations, or for log standard deviations. And so you're parameterizing a diagonal covariance, which is fixed over your state space.
You should make sure it's okay.
Oh yeah.
You said like PPO results are comparable to ACER.
Yeah.
Like, is that in spite of policy of ACER?
Yeah, that's a good question. So question was, if PPO results are comparable to ACER, that seems surprising because ACER is working off policy. So is that in spite of the off policiness of ACER? Well, it seems that seems to be the case. I mean, it's not clear how much it's not clear how much you're learning from the off-policy data in something like ACER, and we don't fully understand these value-based methods anyway, like methods for fitting Q functions. For example, you can't just throw in any like really old data into these algorithms and expect to learn from them. So it seems like there's a limit to how much they're actually learning from the off-policy data. So yeah, right now, yeah, that's what I would say. It's certainly a lot simpler to implement because you don't have to even have a replay buffer. You can do a replay buffer with PPO, and that you can get a bit of an improvement with that. But I found that it wasn't that much of an improvement, so I decided it's better to just keep it simple. Okay, so the first extension I'll talk about is doing self-play training. So this means if, let's say you're not in the usual MDP setting where it's just a single agent trying to maximize its expected return, but now you're in the setting where you have you have a zero-sum game, meaning you have two players in the game, and for one of them is trying to maximize something and the other one's trying to minimize something. So we have two players and they have opposite rewards. So player one's return, R1, is the negative of player two's return. So we could write this out as like this, where player one's trying to maximize this expectation of R1, and player two is trying to maximize the expectation of its reward, R2, which is the negative of R1. So player two is trying to minimize R1. So this is a minimax problem, and we're trying to find a saddle point, which is a point where both players are at a local optimum. And this is also, in this case, it's called a Nash equilibrium. So it turns out that often you can find a saddle point by just doing gradient descent on each of your variables. So you just do gradient updates on each of your variables, and this will lead you to the saddle point. That's kind of a non-obvious fact because unlike your usual single objective optimization, it's not clear what's actually improving every step, or it's not totally obvious what's improving every step. It turns out that for certain kinds of functions, like if one of them if it's concave with respect to one variable and convex with respect to the other, then you actually are you're monotonically decreasing the norm of the gradient. So there is a way to analyze it in some cases, but in most cases it's somewhat of a mystery whether it'll work or not. And it turns out that well, people have recently started to work on doing reinforcement learning in the self-play setting where you have two policies that are fighting against each other. And there are several versions of this. One is you could have an asymmetric task where you have two players against each other, but they have a slightly different dynamic. Like the dynamics are slightly different for the two players. Like you have a goalie and someone trying to score on the goalie in a soccer game. So in these tasks, it's naturally used two separate policies that you're incrementally updating. Then you might have a symmetric task where you have two players that have exactly the same dynamics model, or if you were to swap the players, it would be the same game. In these kind of tasks, you can actually train the policy against itself. So you just have one policy and you're updating it. You play it against itself and you pretend that the other player is part of the environment and compute the policy gradient. Yeah, so in both of these versions of the algorithm, sometimes it helps for stability to train the policy against old versions of the opponent. Otherwise, you might end up, this optimization process might oscillate. Like, let's say you have two players doing rock, paper, scissors. You might have one gets stuck on rock, the deterministic policy of rock, and then the other one does paper all the time, and then the other one does scissors, and the other one switches to rock, and so on. And they keep chasing after each other, and you never converge. So that's one conceivable problem that you might have if you do self-play training. If you play the policy against old versions of the opponent, so basically you're playing against a mixture of past opponents, then you tend to get better convergence properties. So that's what people sometimes do. It's not totally clear that you need to play against a mixture of old policies, though, when you have stochastic policies, when you're optimizing stochastic policies in the first place, because then the policy itself is a mixture of different strategies. So I think the jury is still out on what's the best way to do this, and people have tried various versions. So some of my colleagues worked on this idea of doing self-play in reinforcement learning, where you're training two policies against each other. And these are some of my favorite videos from RL. So here we have the sumo task where they're trying to push each other off of the ring, off of the platform. So you see very lifelike behavior, like getting low to the ground kind of emerges naturally out of this. And they also fake each other out. Yeah, here's the soccer example. They track each other's movement. So the goalie tries to stand in front of the player. And then if you just take one of the policies and you get rid of the other player, you find that it still has some interesting properties, even though this is kind of out of sample. Like it's just has really good balance. Even though it was trained to do wrestling, but now if you just apply forces to it, you find that this is a policy that's just very stable. And the last thing I want to talk about is some recent work on, and this was using PPO along with this self-play training. It was by Trapid Bansal and collaborators. Last I want to talk about using this, well, I want to talk about the meta-learning setting a little bit. So this is some work done mostly by summer intern Kevin Franz. So I'll first just show you the video. So the idea here is we want to learn some kind of continuous control task, but it might take a lot of time steps to do the whole, to complete the task. So to get to the goal. So let's say you want to navigate through some maze. It might take thousands of time steps to get to the goal. So if you just try to use our standard RL methods to solve any given maze, it'll take a long time before you even see the goal for the first time. So it'll take, so training is likely to be really slow. What we want is to be able to learn really fast to solve a previously unseen maze. So the way we set the meta-learning setup is you have a distribution of tasks, and you want to learn something from your training tasks, such that when you see a test task that you haven't seen before, you can learn really fast to solve that test task. So this is a slightly different setting than people usually consider in reinforcement learning, where you just have one task and you're trying to do really well on it. Here we have training tasks and test tasks, and we want to learn something from our training tasks so that you can learn really fast on a test task. So it's called meta-learning because you're learning how to learn. So there are lots of different ways you could do meta-learning. The way we considered is let's try to learn a set of motor primitives such that you can learn a policy on top of those motor primitives, a high-level policy that switches between them. And learning this high-level policy is fast. So the way we formulated the problem is to say you want to learn motor primitives such that the high-level policy can be learned fast. So let's see. I'll show a video so you have some sense of the so you have some sense of the kind of problems we're trying to solve. So what we're trying to learn is a set of sub-policies, that's synonymous with motor primitives. And at any given, and then we want to learn a high-level policy that switches between these sub-policies. So at any given time, one motor primitive is activated, and the high-level policy only changes its action at some longer interval of time, so say every 20 time steps. So every 20 time steps or every 100 time steps, the high-level policy changes which motor primitive it's calling, and then you execute that primitive for 100 time steps. So we want to learn a set of primitives which work well under this distribution of tasks so that the high-level policy can be learned really fast. So in particular, we considered tasks where you have some kind of maze and you're trying to navigate through it. So we have this critter, which is an ant robot, and we want to learn some kind of policies for walking straight and for turning, such that we can switch between these. And if we learn the right kind of switching policy, which is this high-level policy, then we can solve a new maze. So, so you can see here the robot is in just a given maze, and you can see we were on sub-policy 1, and then we switched to sub-policy 2. And here you can see it's going to take advantage of a property of the environment, which is that there's this chomper thing. So it goes over to the chomper, and then the chomper goes and whacks it, and that brings the robot closer to the goal. So this maze problem takes 3,000 time steps to get to the goal, but we set it up so that the sub-policy runs for 300 time steps, and that way you only have to make 10, the high-level policy only has to choose 10 actions. So it's obviously much easier to learn that on a new task than it would be to learn the whole thing. Oh, okay, let's see, okay, that's the whole, I thought I had a longer video. Anyway, so yeah, that's an overview of it, and there's a paper on archive that you can check out for more details. Mm-hmm.
Have you thought about making the length of time that each sub-policy is active and adaptive, like something that I guess is not fixed?
Oh yeah, yeah. So the question is, can you make the length of time not fixed, or can you make that adaptive? So actually, this. Yeah, we didn't do that, but I think that would be a good next step. So there's actually a long line of work with this kind of hierarchical policy setup where you have, I mean, the classic paper on this is on options, or the classic formulation of this is options by Prekop and Sutton and Singh, I think. And so the way they set it up is you have this option, which is like the sub-policy, and the option decides when to terminate, so it can be variable length, and it terminates when some condition is satisfied. So what we did here is like a simplified version of options where it has a fixed time interval, but you could do something more complicated where the sub-policy decides when to terminate and allow the master policy to choose another one. Yeah, something like that. I mean, there are some other papers that have come out recently, there's the what is it? The option critic, where you have you have a neural network that you have some sub-policies, and you have a neural network that chooses to switch between them and to terminate, and they derive some policy gradients and so on for this architecture. Yeah. So it would be possible to adapt some of those ideas to this setting. I think basically the new thing we were proposing here is just how to set up the problem to formalize it as this learning the primitives so that you can learn the high-level policy fast. I mean, one of the big questions for hierarchical reinforcement learning has been how do you set up an objective so that you can get a hierarchy automatically. Like, how do you set up an objective so that the optimal solution has a hierarchy? It's not totally obvious, because if you just set up a single reinforcement learning task, this task has an optimal policy, so there's no reason why you should have any kind of hierarchy. You should just have a policy that optimizes the performance on that task. So it's hard for, so if you just set up an architecture that looks hierarchical, it's not clear that when you're done learning, you're actually going to use the whole hierarchy. Maybe if you set up your architecture to switch between a bunch of different policies, you're just going to use one of them, or there are different degenerate cases. Or you'll choose a different action every time step. So what you want it to do is to like choose a high-level policy and stick to it for a while. And each of your, well, choose a primitive and stick to it for a while. And each primitive is doing something different. But what you might get is you might get a sort of degenerate solution where either you stick to one primitive the whole time, or you switch primitives every single time step. Yeah.
Would it be too difficult? Like, it sounds like you just have multiple networks here, where you have the lower level network and the higher level network.
Mm-hmm.
If you just fed in like the time step
Mm-hmm.
as one of the inputs, then in theory that should be something that the policy learns on its own, like its own hierarchy or something like that.
Uh-huh.
And like, what makes that too challenging for the policy to learn on its own?
Let's see, I don't quite follow why feeding in the time step would
Well, wouldn't you
cause it to learn a
if
hierarchy.
you have a general function approximator,
Mhm.
wouldn't you be able to switch over the time step? Like, if you can do this lower level policy thing, then in theory it should be possible to learn the fact that you have a time step which toggles how your behavior should change based on that.
Uh-huh.
So, yeah, I just don't see what. I guess it's like extra supervision, because you're forcing the this certain breakdown between low-level policies and high-level policies.
Well, I think in the so in the usual setting where you have a single task, then you could and you set up some kind of well, there's an optimal policy for that task. So if you have so you can learn the optimal policy, and it's not clear if it's hierarchical or not. I mean, and it could, if you pass in the time step, then it'll probably use that information. It might use that to define some kind of time varying primitive.
There's just no way to transfer that.
Yeah. The whole point of this was to set up to kind of build in transfer into the problem formulation. Yeah. All right. Well, that's oh, yeah.
Sorry. Going back to PBO, can you talk a little bit about, I guess, the hyperparameters of that, like the step size, the epsilon, like how much that affects things?
Oh yeah. Okay. Yeah. So in PPO, what are the hyperparameters? So there's so one step. Yeah. The main hyperparameter is this epsilon that you use for clipping. So this determines kind of how big your policy update is going to be. And I would say if you, I would say that's, you just need to set that, you need to kind of tune that hyperparameter in order to, well, there's no like very good way to tune it. The problem is the main thing that's limiting, well, basically there are two things you can look at which you're trying to control with epsilon. One is, you should make sure your policy isn't collapsing in performance. So if you're doing too big of a policy update, then you're probably just going to collapse in performance, because you might just do a huge update and you're going to forget. Well, you might like you're optimizing some local approximation of the objective, and you might be leaving the region where this is a good approximation. So that's the first issue. That's easy to check. The more difficult one is that if you're doing policy updates that are too large, then you're overfitting to recent data. And what you sometimes see is that your policy performance will plateau when you choose one step size, and then if you choose a smaller step size, it'll plateau at a higher performance. So what happens there? So it's plateauing where your noise overwhelms the signal. So and if you decrease the step size, then you're kind of you're decreasing the noise, and you're able to converge to a better solution. It's like, I mean, decreasing the step size in any kind of stochastic gradient algorithm is is the same as having a larger batch size. So, so the important step size for PPO, the most important step size is the epsilon parameter. You have another step size, which is the actual optimization step size. So if you're using atom, which is what I usually use, you have a step size for atom. That's actually not as important, because as long as it's large enough that, enough that you're basically converging to a decent solution during your each update, then it doesn't matter so much. So many values will give you basically the same update. But one reasonable criteria is that, let's say you're doing 10 epochs of optimization, and that's fixed. Then you should be, what you can look at is, you can say, I want like 20% of my samples to be clipped after by the end of this, or by after 5. I want like 20% of my samples to be clipped after 5 epochs. So you can use something like that to, some criteria like that to tune your atom step size. Well, basically, you just want to make sure that you're mostly solving this sub-problem each iteration. So if your step size is too large, then you're not going to solve it very well, because your steps are too noisy. And if it's too small, then you're just not going to get all the way to the solution. So you can just look at how many samples are getting clipped, or you can look at the KL between the new policy and the old policy and use that as a diagnostic. Okay,
but you haven't, I guess, it sounds like, you've thought about adaptively scaling things, but I guess it sounds like you say that's not a big deal, really.
Yeah, actually it is. If you're trying to optimize for a long time, it's a pretty big deal. So if you just have a short if you're just optimizing for like 1 million time steps, or just enough to see the learning, happen on a task, then it doesn't matter so much. But if you're trying to if you're trying to learn for hundreds of millions of time steps, then it's actually kind of important, because the problem characteristics will change over the course of this optimization. So you might actually plateau early if you don't have some kind of either a schedule or a sensible way of adapting these things. So actually, one thing we've looked at is adapting the atom step size based on some criteria like what I just described, which is like how long does it take for you to step out of some kind of KL bound.
Like the atom moment estimates, or the base?
You look at either what fraction of samples are getting clipped, or what's the KL, and you use that to adapt your atom step size. So that's something that also helps a bit. You still basically always have some hyperparameter that is hard to choose, which is basically controlling how much you're fitting to the recent data, and that's actually really hard to. I don't think there's a good way to do that I'm aware of. Some way of controlling overfitting to recent data. Yeah, I think that's a problem for SGD, for any kind of SGD kind of method. People just kind of have ad hoc methods for choosing the schedules, or they use fixed schedules where you're annealing your step size down to 0. But I don't think there's a better answer of how to do that adaptively.
Sure. Okay.
All right. Any other questions? Yeah.
I had a question about PPO.
Mm-hmm.
So there's that paper about making deep RL matter.
Oh yeah.
And you had mentioned hyperparameters make a big difference, right? But that paper also talks about different implementations of TRPO and how there's noticeable performance difference.
Yeah.
Is that the case for PPO as well, or is it more stable implementation-wise?
Actually, I would say the differences they found in TRPO are mostly because of how you're scaling the inputs, which is extremely important. Like you have to, like for these, and actually it's important, especially important because for these Mujoko tasks in Gym, the inputs aren't really scaled at all, and they're just crazy, like unscaled inputs coming in. So you need to do something, and depending on how you scale it, that will affect the performance a lot. So I think, yeah, I don't think it's actually dependent on any other details of the, like the mathematical, like, yeah, there's no like significant differences in the actual algorithm. It's mostly about input scaling, and probably there might be some other hyperparameters, but yeah, for any algorithm, you're going to find like a huge effect of the hyperparameters, and so they might have found. Well, I think that paper is nice. I'm glad they wrote that paper, but I think that they're just finding that like the performance is noisy and highly dependent on hyperparameters. So that's the main takeaway. They also found that PPO was kind of more sensitive to the size of the network. So that, I think what that tells you is that when you use a bigger network, you have to also control your epsilon. You have to like shrink your epsilon parameter, because with the bigger network, you're going to tend to overfit more to the recent data. Whereas TRPO, you're only doing this one CG step, so it seems less prone to overfitting, even if you use a big network. Not totally obvious why, but that seems to be one of the non-obvious findings. All right, any last questions?
All right,
All right, thank you.
Thanks, John.
Pleasure. Yeah, it's good to be back.